Hello, this is Ms. DB. In this video we are going to give an overview of polynomial functions. So polynomial functions, this is the general form, but it looks crazy. We have a leading coefficient a sub n times x to the n power, that's our leading term, and then from there you're just going to go in decreasing order. So the next coefficient times the next variable with one less, or with a smaller exponent than the first one, and so on. Here's an example of polynomials. They look a lot simpler when you just write the examples down. So it's interesting to note that linear and quadratic functions are really examples of polynomial functions. They're just a part. Like here's the linear function, and if you expand that just a little bit more, here's your quadratic function. So they will have a variable, and the variable can just be x, but then it's just a linear function, or it could be x squared, but that's quadratic, and we've already looked at linear and quadratic. So we're really going to be focusing on cubic polynomials and higher terms. So here we have a cubic with a negative 3x to the third power plus x minus 6. This one, it doesn't look like it's a cubic function, but if you were to multiply x minus 3 times x minus 3, you'd get x squared times 2x, you would get an x to the third power. We can have 2x to the fourth, that's called quartic, or even quintic, which is x to the fifth. After that we would just say what degree the term was. So polynomial functions, there's lots of them. We can't explain everything about just one of them without, realizing that there's lots of different options. So these are some of the polynomial functions. We have a constant function that has a degree of 0. It's just a horizontal line. A linear function has a degree of 1. A quadratic function would have a degree of 2, like x squared. And then here's the kinds that we'll be looking at today. We have a cubic function, which would have a degree of 3. A quartic would have a degree of 4. A quintic would have a degree of 5. So look at the cubic. It is going to have this nice kind of a zigzag pattern to it, and it might cross the x-axis 3 times. It might have a y-intercept and an x-intercept, like in this case that happens to be a y-intercept is right about there, and it's got 3 x-intercepts. A quartic function often looks like this W shape, but sometimes it just kind of looks like a wide quadratic. It kind of flattens out somewhere. And a quintic can look like this with lots of zigs and zags, or it can look different than that too. It really depends on what numbers are in front of each of those and what signs you have. Polynomial functions can be one of the few functions that you can determine the end behavior without looking at the graph. You can look at the leading coefficient a, and you can look at whether it has an odd degree or an even degree. So an odd degree would be like x to the third power, x to the fifth power. An even degree would be like x to the fourth, x to the second, of course. And they behave differently depending on whether they have an odd degree or an even degree, and whether the leading coefficient is a positive number or whether the leading coefficient is a negative number. So if you have a polynomial, like a cubic or a quartic or some degree polynomial, you can look back at this chart to help you decide what's happening for the end behavior. And end behavior, remember, is what's happening as the x value increases, what's happening to the function. So in this one, the y value is also increasing, so it's going to infinity. And what's happening as x gets smaller and smaller, in this case, it's going to negative infinity. The domain of a cubic or a fifth degree or an odd degree is all real numbers, and the range is also all real numbers, unless there's some limits placed on it by the situation or a word problem. And for an even degree, the domain is still all real numbers. That's what this fancy R means. But the range will have, there'll be a minimum if the leading coefficient is positive. There'll be a minimum point. So like when we looked at a quadratic, it will be y is greater than or equal to some number. Or if it has a maximum point, then it'll be y will be less than or equal the y value of that maximum point. And then a little bit more about maximum minimum. We've talked about these before. Global is also, I usually call it absolute, but global is fine too. The absolute max is the highest that this graph can ever be. This one's going to negative infinity on both ends. But there's also a local max. If we look at just this region, we can see that there's a bump there, and there's a local maximum right there. So you can find local max as well as absolute or global maximums. This one does not have an absolute minimum because it's going to decrease on both ends for both end behaviors. But we do have a local minimum right here. We don't usually write that the absolute minimum or absolute maximum is infinity or negative infinity. We would just skip that and not answer that, say there is none. Okay, and then roots and intercepts, like we talked about when we talked about quadratics, the X-intercepts are also known as the solutions or the roots of the problem. If you have a polynomial and you have an intercept that just touches the x-axis, that's going to be where there's a double root. So if you were factoring this polynomial, which we did when we did a whole chapter on polynomial functions, we factored, and we would find that x minus 2 and x minus 2 would both be factors of that polynomial. There'd be a double root there. And then if it just goes through, then that's just a single root. The y-intercept is probably easiest to find just by graphing and looking at where it's crossing the y-axis. It's not always the minimum. In this one, it's not the minimum. It looks like the minimum would be a little bit over here. So the y-intercept might not mean as much as it does in some of these problems. And one more thing to talk about. Oh, first of all, if you put the max, minimum, intercepts, x-intercepts, and y-intercept, if you put them all together, that's called the critical values. And then I also want to talk about concavity, which is concave up or concave down. It's easier to see in this one here. This part is concave down. If it was raining, think about raindrops here, you would not get wet underneath the concave down part. But the concave up part would be catching the rain and it would be filling up. So it's concave up if it's holding water, it's concave down if it's shedding water. The place where concave down switches to concave up, or vice versa, is called the inflection point. Some graphs have inflection points, some don't. Quadratic functions don't have inflection points, but cubic functions do. It also might be a little less obvious, the concave down and the concave up, but you can still see that if it was raining, you would stay dry right here. You'd be happy, you wouldn't be getting wet. But if you were here, on this side, you would be getting rained on. So this is going to hold, maybe not hold the water, but it would catch it and not protect you from the rain. So I added some notes here about, in general, polynomial functions. They will not have asymptotes. We'll look more about asymptotes when we talk about some other functions, but polynomials don't have asymptotes. The domain is usually all real numbers, like we talked about. And the range, if it's an odd degree polynomial, will be all real numbers, but in even degrees, it'll be either y is greater than or equal to some number or y is less than or equal. Cubic functions will have one inflection point, but higher degree polynomials may have more. Not always, but they may. In this one, we would have an inflection point about here, because this is concave up, and then it switches to concave. Oh, actually, the inflection point would be about right here, where it switches from concave up, and then now here it's concave down, and then there's another one about here, where it switches back to concave up. So I counted 2 inflection points in this one. So they can have more than one inflection point. They may or may not have symmetry. If they have symmetry, if it's an odd degree, it might have symmetry about the inflection point, or it might have symmetry about the origin. If it's just the parent function going like this, you can kind of see how you could take this piece, cut it off, and rotate it about the point, and it would end up here. That would be That would be symmetry about the origin. Or it might have no symmetry, or it might have symmetry about a line, especially in like as we looked at with an even degree, they have symmetry about a line. And sometimes quartic functions might have symmetry about a line as well, a fourth degree function. And so what you're going to do is for 1 and 2, you're going to answer all the questions you can about the two different graphs here. And then in number 3, you're going to graph, there's an extra number there. You're going to graph x to the third plus 4x squared minus 8. You can use Desmos to do that, and then answer all those questions about maximum and minimum, domain and range, and so on. And then finally on this part about polynomials, we're going to practice finding the roots with algebra. The easiest way to do this is by factoring. So for these problems, the first one has already been started. I start by factoring out the greatest common factor, and then what's left we'll try to factor. So let's look at number 6. Let's see, I could factor out a 2 and an x from every single term. And if I did that, I would be left with x squared, and I'm factoring out a 2 and an x, so I would be left with 6 divided by 2 is 3x, and then 36 divided by 2 is 18, and I already factored the x out. So I'd be left with x squared minus 3x minus 18. So now I'm going to try to factor these with trinomial factoring. So the first term in each set of parentheses would be x. I'm just going to switch to a pen here, I think. And then I'm looking for the factors of negative 18 so that when I add them, I would get negative 3. So negative 3 and 6 would be, if I added these together, I get a positive 3. So let's do a positive 3 and a negative 6. So I'd have plus 3 minus 6. And then I'm going to set each of these factors equal to 0, including the greatest common factor. So 2x equals 0, x plus 3 equals 0, and x minus 6 equals 0. And solve each of these, and you will get 3 answers, and those will be the 3 roots of your polynomial. And the great thing is you can graph this, and you should find that those roots agree with where they cross the x-axis, the x-intercepts. And there's just a little bit more about multiplicity of a root, and I'll let you look at the example and do just 2 more questions about that. All right, thanks a lot. Have a great day.